on, and we'll continue this experiment. I apologize for that interruption. Isaiah, Trevor, Jared, Brandon, Matthew, Camilla, welcome everybody. As you can tell, I hope, from the screen, I'm asking, are there any questions? I had one, I think, from Camilla, number 29, so I'm going to do that one first. Anybody else, think about what you want to ask about, and we'll get that going. So here's 29. So 29 from 1.4, the question, the directions were evaluate the difference quotient and simplify. So on 29, they gave us the function 1 over x minus 2. And you know, I don't have the room to write the difference quotient out, but you know that what I'm looking for is what? You can either, the way they write it, they want you to use the delta x formation. So we need to find f of x plus delta x minus f of x all over delta x. And in order to do that, we know what f of x is. We just have to find this f of x plus delta x. And you remember the way to do that. Welcome, Maki. Sorry you had to come back. Glad to have you. We're going through question 29 on lesson 1.4. So before we can do the difference quotient, we have to find f of x plus delta x up here at the top. I gotta, let's see, get my keyboard off right here so I can write on the screen. All right, so still having interesting difficulties here. Let's get that mouse out of there. Okay, all of a sudden, no pen action. Interesting tech day. I don't know what's going on here. Take my mouse out, see if that helps. Nope. There we go. Okay, finally we got some action. Sorry about all these challenges today. So, hopefully you can all see how all I did was plug in x plus delta x for x, and I got this thing in the blue circle here. So now, here's the different, let me put this in red. Whoops. Let's try making that into a box. Well, it's not in red. But in the box, that's the difference quotient. Over here on the left is f of x plus delta x. Over here on the right is f of x. And you put that all over delta x. Well, before I can do anything, I got to get these two fractions together on the top. And so I need a common denominator. And I think you can see the common denominator is just what? Each denominator. So in the first one, I need the x minus 2, so I multiplied top and bottom by that. On the second one, I need the x plus delta x minus 2, so I multiplied top and bottom by that. And that gives me this thing down here in that box. All I did was put the common denominator underneath and then multiply out the numerators. Please notice I had to put parentheses around this second thing here, making stray boxes. I don't know why. But now, instead of dividing by delta x, I did this. I did this right here. So if you divide by delta x over 1, isn't that the same as multiplying by 1 over delta x? Okay. When you simplify the numerator, the x's go away, the negative 2's go away, and all I have left is a subtracted delta x. On the bottom, I just have my common denominator along with the delta x from the right here. You can cancel the delta x's, and then what's left on the top is just a negative 1 over that denominator. Camilla, I do have to, and anybody else, can you guys see that whole fraction on the bottom? Because one of my screens, I can't see the denominator. Can you guys see that? Just tell me that, somebody.
No, it gets blocked.
It is blocked?
Mm-hmm.
Now it's not. Okay. So it's just, does that make sense, Camilo?
Yeah.
Other questions from 1.4, anybody? You know what, I think I can get rid of those pictures at the bottom, except my mouse isn't working. Well, it's an interesting day for tech, guys. Try plugging my mouse back in. We'll see if we get any action here. Can you guys hear me now? Okay, we're back on. I'm sorry about that. I tried getting rid of the pictures on the bottom and it goofed things up. So hopefully all of you can see and hear now. So anyway, we got 3 circles on the screen, and inside of them are equilateral polygons. The top one has an equilateral triangle, 3 sides, and then bottom left equilateral, we have a hexagon, 6 sides, and then I think it's a decagon. And here's what I'm trying to show. If I keep putting more sides on the regular pentagon, do you see that the regular pentagon is getting rounder and rounder, and it's looking more and more like the circle? And in fact, what's the limit? If there was such a thing as an infinite-sided polygon, wouldn't it become the circle? That's kind of the concept. Yes, this is lesson 1.5 we have begun. Some of you lost the audio there a few minutes ago. Amaki just asked a question. Good question. I am introducing lesson 1.5 now. We're trying to get ready for limits. So do you see in this picture? Do you see in this picture that as I get more and more sides on the red polygon that's inside the circle, the polygon gets rounder and rounder? Okay, I'm sorry for those of you who I had to reboot my computer. We had some problems, and that's why it wasn't such a nice smooth start today. I apologize. We went through one question on lesson 1.4, and now I'm starting lesson 1.5. So this first little lesson here, as you take more and more sides to the red polygon, it gets rounder and rounder, and as a limit, it's kind of approaching a round circle. That's a little bit of the concept of a limit. Now, take a look at this. And I want to just, did I miss? Yeah. Okay, so now look at this slide. And you see we have some ordered pairs here. We have f of 1.9 is 0.4121. F of 1.99 is 0.4012. F of 1.999 is 0.4001. What does it look like we're heading toward when we get to 2? It looks like we're heading 0.4, doesn't it? How about on the other side when we go bigger? Do you see how those numbers are approaching 4.4 from the other side? So they're kind of squishing in. It looks like the limit from both sides appears to be where the thing is headed, appears to be 0.4. That, again, is just a rough concept of what a limit is. So now we're going to take a look at a function here. And this is one of those piecewise functions that we talked about a couple classes ago. Remember that? It's literally a function made up in pieces. Why is this? This is still a function, though, isn't it? Because it passes the vertical line test. But now, here's what I want to ask you. If you were traveling along this left branch here, let's say kind of in this direction. No, I can't. It's interesting, when my mouse is plugged in, I can't seem to get my, wow, interesting problems today, guys. Sorry about all the buzzing and everything. But anyway, as I'm approaching, as I'm kind of going this way on the blue line, where am I headed to? It seems like I'm headed to, I see that whole thing got moved. Golly. You name it, it's going wrong today, guys. But anyway, it seems like I'm approaching the height of 1, doesn't it? As I get closer to 2. Well, what if I'm traveling from the right side on this branch and heading to the left? Where is that heading to? That seems to be heading for the height of 3, doesn't it? So what I'm trying to show you is on this problem, on different sides, we're heading to a different place. Okay, here's what some of the notation looks like here. I know this is new to many of you. This first statement here says the limit of f of x as x approaches 2, and that little minus says from the left side. So as I'm approaching x equals 2 from left, what height am I approaching? 1. So, one more time, that reads, the limit of f of x as x approaches 2 from the left is 1. But from the right, that's you can ignore this one for a minute, but this one here says the limit of f of x as x approaches 2 from the right, that's what that little plus means, that limit is 3. So when I'm coming from the left, I'm approaching a height of 1. When I'm coming from the right, I'm approaching a height of 3. So because we're not approaching the same height from both sides, we say this function does not have a limit. So in other words, the left-hand limit and the right-hand limit do not agree. Whenever that happens, we say the limit does not exist. And we often abbreviate that DNE. So, what I know this is a little bit unusual, but here we have a function that's doing something different on the left side than on the right, and they whiff. So the limit as we're approaching from the left side to go to 2 is one thing, and as we approach it from the right side, it's a different thing, and that's what these two statements say over here. Over on the right, it says the right-hand limit is 3, the left-hand limit is 1. They don't agree, so overall, what's the limit of the function as x approaches 2? It doesn't exist. DNE does not exist. I know that's new notation. It'll take a little while to get used to. Yeah, so summarized, if the left and right-hand limits do not agree, then we say the limit does not exist. And we say the function is discontinuous. In other words, there's a break in it. And I know you guys could have seen that immediately just by looking at the graph that it doesn't exist. But anyway, now we have the official statement. So, okay. Now, and this is where I was going to experiment with a little bit. I have these little mini website kind of videos that I want to share. By the way, they're all linked on your website. If you go on the Moodle page and go down to lesson 1.5, which is what I'm working with you on right now, you will see there are 5 little videos there. And you can just click on them and play them. So if this doesn't work, well, we'll find out real quickly. Okay, so what I'm going to do then is I'm going to click on this link, and then I'll have to goof around a little bit and share a different screen with you. Okay, Maki, I don't know what your question is. Limit, DNE, and function is what? Okay, let me try to clarify. The function in this particular example is this blue curve that's in 2 pieces. Okay, that's f of x. And in this case, the left-hand limit as x approaches 2 is not the same as the right-hand limit. When the 2 limits do not agree from either side, then we say that the limit does not exist. And the abbreviation for not exist is DNE. Okay, yeah, I don't know, Maki. You maybe should, if you're connected live, it doesn't. Yeah, you are. Why don't you turn your mic on and then we can communicate at a maybe a better speed. Go ahead and ask me your question, Maki.
I get it, so it's okay.
You do get it now?
Mm-hmm.
Yeah, that's what I thought. I was a little behind your questions, and thank you. That
I just wondering, like, function is discontinuous, and I did not see the discontinuous part. So.
Okay, thank you for responding. All right, so now let's try one of these videos. I'm going to click on the link, and then it'll take me a few seconds. I've got a web page to open up. Then I have.
You may have heard a lot of talk about limits.
Now I have to share this screen, so hang on just a second. Okay, which one is it? Screen 1. Help.com. Okay, I believe you guys are seeing this web page now. It says calculushelp.com on the top. Now, what I don't know when I restart this little video, if all of you are going to hear it, so I want to get some feedback on you, but here we go.
But the plain fact remains.
Let me restart.
Most people don't understand. You may have heard a lot of talk about limits, but the plain fact remains. Most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
So first of all, can you guys hear that? Did the audio get through? Okay, thank you, Camilla. Good. So I'm going to continue now. So it's kind of weird, but the limit of a function is what height it kind of intends to get to. Okay, now I'm going to just continue the video.
Let's start by a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4.
Pretty straightforward so far.
There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
So you see now you see maybe why they said the height that a function intends to be. So the graph that we just looked at was heading at that point, but even though it had a hole in it, it was still heading there from both sides. So that's okay. It's like, yeah, that's where it was aiming at. That's where it wanted to go, so that's a limit. Now, when the two sides don't agree, well, that's a little different matter. And anyway, I'm going to go back now. We won't get this lesson done today, but I do want to get a start on it. I know this is different, so hang in there. And by the way, this is what the calculus help website looks like. We just did this first one here, what is a limit? And now let's do lesson 2. When does a limit exist? If I can, I thought it was a link, I guess not. So what I'm going to do is go back to my slides where I have that. And you won't see any, I know you're seeing my ceiling for a moment here, but that's okay. We'll be back. Actually, I think yeah, this is kind of hard switching back and forth, but I don't have much choice right now. So what I'm going to do is let's share back with my, no, I can't. Okay, we're going to be in trouble here with this resharing because I've lost my share screens again. Guess we're just asking a little too much with those videos in there today. I can't share again, so we're kind of in deep trouble. I mean, I can change my screen so you can see me, but that doesn't help. And by the way, if I wrote on paper and showed you what I had, you would notice that it's backwards. So, my apologies. I guess what we're going to have to do is I would like you to do some reading, and if you go onto the website, you'll see all kinds of things, including all 5 videos I was going to show you today. So I'm going to give you that assignment. Go in there and click and watch those videos. Okay? Also listed on the website, if you keep going lower on lesson 1.5, is the assignment. And even though I'm not ready to give it, you might want to get started on it. Yeah. By the way, you should be hearing me again. I didn't mute it. And Mason, don't mute me again. Okay? Anyway, I'm trying to get the website up. A little bit slow with all the stuff I'm loading here. That's okay, Mason. Don't worry about it. Yeah, I'm just having bandwidth issues here, and I'm having trouble connecting, and I think, you know what? I'm going to check one more time to see if I can share. Yeah, once that's gone, I can't seem to get it back, and that's why we had to stop the first time. Anyway, you guys are going to have to look it up. If you go on the website, you'll see what the assignment is. It is not due next time, not due tomorrow, but try to get into the videos and start on the assignment. I will spend another day teaching this. I'm sorry this didn't work out so well today. This bouncing back and forth, sharing different things, what was challenging. So I apologize. Thanks for hanging in there, guys. And I guess we're going to have to call it quits today. Thank you.